All right, let's talk about what is quite possibly the single most fundamental rule in the entire universe. Seriously, it's the hidden reason your coffee gets cold in the morning, it's why the stars shine at night, and it's why time itself feels like a one-way street. We're diving into the second law of thermodynamics.
So, let's dive right in with a little mystery. Something you've seen 1,000 times. There's a reason some things just happen in one direction, and one direction only. It's what gives us what scientists call the arrow of time.
I mean, think about it. We see eggs break. It's a daily occurrence for some of us. But have you ever, not once, seen the reverse happen? Have you ever seen a gooey, shattered mess of shell and yolk just leap off the floor and magically reassemble itself into a perfect egg? Of course not. The idea sounds completely absurd, and there is a very deep physical reason for that.
And look, this isn't just about breakfast mishaps. This simple fact that broken eggs stay broken. It's pointing us to one of the biggest, most profound questions out there. Why does time seem to flow forward? Why is the universe a one-way street and not a two-way highway?
Well, the answer isn't some weird philosophical idea. It's a rock-solid, cold, hard law of physics. It's the second law of thermodynamics, and you can think of it as the universe's ultimate traffic cop. It stands there directing the flow of everything, and it says, very clearly, no U-turns allowed.
Okay, so to really get our heads around this law, we have to introduce its main character. It's a concept called entropy. This single idea is the key to unlocking the secret of the broken egg and, well, pretty much everything else.
So what is entropy? The simplest way to think about it is as a measure of disorder or randomness. The law says that in any isolated system, and that's a key phrase, think of it like a perfectly sealed thermos that nothing can get into or out of, the total amount of disorder can only go up over time. It never, ever goes down. On the grandest scale, this means the universe as a whole is always, constantly getting messier.
And you know, this incredible idea didn't just pop into someone's head overnight. It was a real journey. It started with something super practical. People in the 1820s trying to build better, more efficient steam engines. Then, in the 1850s, a guy named Rudolf Clausius gave this tendency towards disorder its name, entropy. And finally, a physicist named Ludwig Boltzmann tied it all together, explaining it as this kind of statistical dance of zillions of tiny atoms.
Okay, let's make this feel a little less abstract. Picture a brand new deck of cards, all in perfect order. That's a low entropy state, super organized, or a clean room, or a perfect ice crystal. Now shuffle those cards, mess up that room, let the ice melt, boom, high entropy. And why does this happen? Well, think about it. There's really only one way for those cards to be in perfect numerical order. But there are, well, trillions upon trillions of ways for them to be jumbled up and messy. Nature just plays the odds, and the odds are overwhelmingly in favor of the mess.
So this isn't just some weird thought experiment about playing cards in messy rooms. This law has real, tangible consequences. You can think of it like a fundamental tax that nature charges on, well, on everything. Because entropy is always on the rise, it means that no machine, no process that turns heat into useful work can ever be 100% efficient. It's just not possible. It's a cosmic speed limit you can't break. And once you start looking, you see this rule everywhere. It's why your hot coffee always cools down in a chilly room and never the other way around. It's the reason perpetual motion machines are pure fantasy. It's the hard limit on your car's fuel efficiency and why so much of that gasoline just becomes waste heat. Entropy is like this universal tax on every single energy transaction, and it's absolutely non-negotiable.
All right, so we've seen it in our coffee cups and our cars. Now, let's zoom out. Let's take this law and apply it to the biggest stage imaginable, the entire universe. And this is where the implications get, well, they get pretty mind-bending.
Way back in the 1860s, Rudolf Clausius, the same guy who coined the term entropy, he made this incredible, bold leap. He figured if this law applies to every sealed-off system, then it must apply to the ultimate sealed-off system, right? The universe itself. And if you follow that logic all the way to the end, you get to a pretty bleak and chilling idea, what's called the heat death of the universe. It's a picture of the far, far future where entropy has finally, completely won. Everything is evened out. Every star is burned out, all the energy is spread perfectly thin, and everything is the exact same lukewarm temperature. Nothing can happen. No work can be done. No life. Just a silent, uniform, eternal stillness. Okay, but wait a second, hold on. If the whole universe is just winding down, getting messier and more disordered, then what about us? What about life itself, which seems to be the exact opposite of that?
Yeah, it's a great question, right? Because when you look around, you see these incredible pockets of order. A single cell, a tree, the human brain. I mean, these are masterpieces of complexity and structure. It really looks like life is thumbing its nose at the universe's prime directive to make a mess.
So how do we solve this paradox? Well, the key is remembering that little phrase from earlier: the rule only applies to isolated systems. But life isn't isolated. We exist in open systems. We're not in a sealed box. We're constantly swapping energy and matter with everything around us.
And that changes everything. See, life doesn't break the second law. It's a perfect expression of it. Living things are basically entropy-generating machines. We build these tiny, beautiful, temporary pockets of order, our bodies, by pulling in high-quality, low-entropy energy, like sunlight or food. And what do we do with it? We use it, and then we dump a whole lot of low-quality, high-entropy waste, mostly heat, back out into the universe. So for the price of our own local order, we actually increase the total disorder of the universe by a whole lot more. The law's perfectly happy.
And this really gets to how non-negotiable this law is. The famous physicist Sir Arthur Eddington said it best. He basically said that if your pet theory goes against relativity, the experts might find a way to make it work. But if your theory is against the second law of thermodynamics, well, you're toast. There's nothing for it but the collapse and deepest humiliation. In the world of physics, this is the one law you just do not mess with.
So what does this all mean for us? If we live in a universe governed by this supreme law, one that's always inevitably sliding towards disorder, what does that make us? It means that every beautiful thing we create, every complex thought we have, every living, breathing organism, it's all just a temporary uphill battle against an unstoppable cosmic tide. These are fleeting little islands of order in an ocean of chaos. And maybe that's what makes them so incredibly precious.